Thank you for the introduction. So the talk will be about active matter in the regime where the density of the system is very large. So there's competition between crowding effects and activity, and we'll see what the physics is about. So before starting, I would like to thank the collaborators for the work that I'm going to present today, and of course the organizers, Pinaki and Arnav, for putting together the conference and inviting me. So I said this is going to be about active matter in the dense regime. So just a few slides of introduction. Why do we care about active matter in the dense regime? So this is a figure that I take from a paper that's a review on the glass transition. So usually in the glass transition talks, I give examples of active systems as applications why glass physics is interesting. So these are dense assemblies of things. So the things can be colloidal particles, they can be cells, they can be ants. So these two guys are clearly active systems, and what you see is dense packings of these things. They form these amorphous solids, and this is the transition between the fluid and this amorphous solid is the topic of the glass transition. So clearly these two examples are examples of active matter in the large density regime. So just to at least warn you to this topic. So what I think an experiment that has made this connection very explicit is this already 12 or 13 years old experiment on epithelial tissues by the group of Dave Waits, where they looked at the dynamics of these dense epithelial tissues, and they made the connection, at least qualitatively, to the fact that in this dense regime, if you want to move, you have to move collectively, and this is the flow field for these systems, and they made the connection to the dynamic heterogeneity that we have discussed a lot in the context of glassy systems. So in a sense, what I want to say is that this type of interesting collective motion emerges a lot in dense systems in the presence of activity, and maybe there are connections to a physical system that undergo this fluid to solid glass transitions. So if you look at this system, it's a clearly very well-packed system. These cells are maybe 20 microns, so they cannot be sensitive to thermal motion. So when you look at this picture, that should remind you of dense emulsions, mayonnaise, something that should behave as a solid. And yet, if you see how it's moving, if the movie starts very slowly, this is what you see in your experiment. This dense system that should be solid, actually, you see motion that resembles fluid. This is a very dense suspension of bacteria, very well packed. And again, because the bacteria can swim and everything, you see the emergence of these motions. So clearly these systems, when, I don't know why this is so slow. These systems, in the presence of activity, they flow like fluid, and yet in the absence of activity, they should be solid. So it means somewhere there must be some phase transition between the fluid and the solid that's driven by the amount of activity in the system. And this is the type of question that I think is interesting in this field. What is the competition between this activity and the crowding? The crowding wants to make the system solid. Activity wants to make the system fluid. What type of phase transition, physical effects, competition, length scales do you find in this system? So that's the general topic of the talk. Okay. So this type of interesting collective motion that you saw in the movie is slowly emerging as a field. So it's called active turbulence. And this type of chaotic flows that you've seen in the movie, they have been observed all over the place in the fields of active matter. So last year, Jean-François Joanny and Ricard Haller tried to organize a little bit. So they displayed in this review article many experimental systems that display these chaotic flows. And they try to organize models according to symmetries and main ingredients of the field. So they decided that there was something like 4 universality classes, potentially, depending on 2 types of things, whether your order parameter would be polar or nematic, and whether or not you have hydrodynamics or no hydrodynamics. So it makes 4 different cases. And they say, let's try to organize the experiments among these 4 places. And I have to say, in these 4 corners, one corner has been studied a lot. It's the dry active nematic study, the Turner 2 equations. They have been solved a lot to understand, the emerging properties of these chaotic flows. In this discussion, you will never see discussion of particle crowding. This is what I want to discuss today. So if I put density effect into the goal, maybe there would be more than 4 universality classes, and this is what I want to show in the rest of the talk. Okay? So we have to go into models and systems and what is activity and what is crowding. So So one system that I like to study and that everybody or lots of people have studied is self-propelled particles. So I'll show you the model again in 1 minute. So this is a model where you have a Langevin equation. So this is velocity, interparticle forces, and you replace the noise term of the usual Langevin equation by something like this. So this is the Ornstein-Uhlenbeck active particle model, where clearly here the noise becomes colored, but you don't have the friction, so you break detail balance, so you break the FDT. So this is a driven system. This thing has a persistence time tau p as given by this differential equation. So this is a persistence force. So for the single particle, you would have persistent Brownian motion, that is self-propulsion. So if you take this very simple model, what you have is, of course, because of the interparticle, you have the crowding effects, density effects will matter, and you have the drive by the self-propulsion. And so this model, although very simple, it's already quite complicated. And many people have tried to understand the physics and the competition between propulsion and density. So this is one example of activity, self-propulsion, but as we heard already quite a lot in this talk, activity can be many more things. So one type of activity that you know is if the self-propulsions here, you see they are totally independent, so the propulsion of particle I and particle J don't talk to each other. So of course, the models of flocking have interactions between the self-propulsions. So when you have aligning interactions between the self-propulsions, you can have these transitions towards pneumatics and or flocking. If you consider biological tissues, the particles or the cells they can die, they can be growing. The bacteria, for instance, they can grow and divide. So this is the field of growing active matter. It's another source of activity. The particles in tissue, they also can actively deform, so the deformation is something also interesting. And we'll talk at the end about non-reciprocal interactions. That's currently quite intensively studied. If you think of birds that have a vision code, then the interactions cannot be reciprocal. And again, if you have non-reciprocal interactions, that's the source of momentum, and you can have interesting motion because of this. Okay, so these are different types of activity. Similarly, crowding can mean many things. So in the field of dense system, we talk about the glass transition, the jamming transition, the yielding transition in different contexts. And all of this then can compete with the different type of interactions. So if you mix these three things with these four things, then you can have different physics. So the activity and the collective motion doesn't necessarily come from a single explanation. It can be many different mechanisms. And the physics, it can be very rich. So this is what I want to do today. So I would like to give you, I think, 3 chapters of this competition between crowding and activity. And so let me start with the first one. So the first one is the simplest case that I showed you before. So the case where you have density and you have self-propulsion. And we heard about this in the talk of Saroj on Monday. So I go back to this model where you have the Ornstein-Uhlenbeck process for the propulsion forces. So here, clearly, the noise is then colored with the persistence time that's tau p. So if you think about it a little bit and you solve the Ornstein-Uhlenbeck equation for the propulsion, you put it back. So you see that the typical amplitude of this persistent force will be given by the ratio of these two things. And the noise will have a persistence time. So whereas in the ordinary Langevin equations, the noise would be wide, so it would have no time scale. It would just have an amplitude, which is the temperature. Here, the control parameters are 2 instead of 1. And so if you want to study the phase diagram of that system, you have to compute a 3-dimensional phase diagram where the density is competing with these 2 parameters that control the amplitude of the force and the persistence time of the force. If you send the persistence time to 0, so you send this term to 0, you see that Pi is this noise. And if you put the noise here, you get back to the Langevin equation that you know. And hence, if tau p goes to 0, you're left with 2 parameters, and the 2 parameters are equivalent to density and temperature, and this is the phase diagram that we study for equilibrium fluids. Okay? So now if you promote this to a self-propulsion, you have a 3-dimensional phase diagram to study, and you have to study the effect of these 2 parameters against the density to understand what it's doing. Okay, so typically we show phase diagrams in 2 dimensions or 3, so we have to think about what do we keep constant, what do we change. And so we discovered after exploring the 3-dimensional phase diagram that a good way to show the physics is to fix one of the 2 parameters, in particular d0, vary the persistence time, and show the result as a function not of the persistence time but the persistent length, which is the combination of the two. in this representation, so D0 is fixed, you fix the persistent length. If you take different cuts at different T0, then the phase diagram essentially doesn't change. So it's a good representation of the three-dimensional physics. If you take a cut, it's essentially independent of D0. So what are the phases that you can have? So this is density, this is persistent length. So again, for non-persistent system, what you have here is the physics of the equilibrium system. If the system is a little bit persistent, it's a self-propelled liquid, so it's a non-equilibrium system. And so this is the self-propelled liquid. If you compress that system a lot, then you will undergo this fluid to solid phase transition towards amorphous Aristide state, so glass transitions. If your density is a bit intermediate here and you increase the persistence a lot, you go to this motility-induced phase separation that have been discussed a lot. So this liquid, this phase separation between the gas and the liquid. And this is typically the topology of the phase diagram. So this phase diagram was measured by my student Jan for WCA Wicks, Chandler, Anderson steep repulsions. And many years ago, I think Silke also studied the model for maybe Hertzian or harmonic spheres, I don't remember, but the topology of the phase diagram was essentially the same. So you have these three phases, so different types of phase transition. So MIPS has been discussed and studied a lot. I won't discuss it. So what I want to discuss is really this blue line. So when you go to large densities, what's happening? This way. Okay, so what I start by doing, I take a weak persistence, so I go back to this one. So the persistence is somewhere here, and I'm compressing the system here. And I'm just watching how the particles are moving by measuring the mean square displacement. So this is the dilute system, that is the persistent random walk. And then if you compress the system, you see this two-step relaxation, a diffusion constant that decreases dramatically. So this is just a fluid transforming very solid into an Aristide solid. So this resembles very much the equilibrium glass transition, as we heard again on Tuesday by Saroj. Yet, if you start to ask questions about how do you predict things, how do you construct a theory for this glass transition, maybe you know that people in the field of the glass transition always claim that it's a difficult problem. So this problem is even more difficult because you're losing all the tools from equilibrium physics. And we heard a little bit about this. So we know, for instance, if you want to construct a dynamic theory, then you can have a fluctuation dissipation theorem. But even worse than this, if you look at the theories of the glass transition, they often start by importing results from the good old liquid state theories to describe the pair structure of the liquid. If you put a little bit of self-propulsion, you don't know how to predict the pair correlation function anymore, and liquid state theory is no longer available. If you think about, again, theories of the glass transition based on entropies and free energies, you don't have those anymore. So you're lost because all your tools are gone because you're out of equilibrium. Okay? So even though it's a non-equilibrium analog of the equilibrium glass transition, it's way harder to deal with it theoretically. So it's interesting. And there are very interesting differences. So this is a non-equilibrium form of a glass transition. Yet, if you approach the glass transition line and you see how the particles are moving, just as in equilibrium supercooled liquids, you will have these large-scale dynamic heterogeneity. So this is displacement fields for how these particles that are self-propelled at large densities approaching the glass transition. And you see these interesting patterns of collective motion. So here, in that case, you have a form of collective motion, and it emerges from approaching a non-equilibrium glass transition, so the competition between self-propulsion and density. And this is really very much analogous to the good old dynamic heterogeneity in supercooled liquids. Now it's driven by a non-equilibrium color noise, if you wish, so it's a bit different qualitatively, but yet the physics is a bit the same. Okay, so these are the simulation studies, so at least I wanted to show this data. So what you see here is, again, something like a displacement field. The particles here are colored according to the displacement over given lag times. But these now are experiments taken on real bacterial things. So this is a two-dimensional bacterial assembly. The density can be controlled in these experiments quite easily. The relaxation time is increasing as you increase the density. So the system is heading towards the glass transition. And by doing this particle tracking, my colleagues Martin and Max have been able to detect this growing dynamic heterogeneities in these bacteria. So this is really the exact analog of these results from computer simulations. I have 2 questions. So you're second, and he was first? Okay. 3 questions.
So Maxine's experiments.
Yes?
When I looked at the data years ago, it seems like at least locally there is a reasonably strong nematic correlation and also a tetratic correlation if you look at it carefully.
Yes.
So both of those could matter.
Yes. So what we've done is they have computed everything. So they've looked at the nematic order. So typically you have 4 bacteria like this because this is the size ratio they have. And these heterogeneities that we detect seem to be relatively unrelated to those.
Okay.
So they say this is present, you're right, but it doesn't seem to affect the physics that I'm discussing.
Okay. And about the growing correlation length of velocity correlations.
I haven't talked about velocity.
Sorry?
I haven't taled about velocity in these models yet.
The previous slide.
No, these are displacements, not velocities.
Okay, fine.
Sorry?
It's kind of like velocity.
Well, its velocity is integrating over large time. So it's a bit not true because if the persistence time is finite, I was looking at extremely large times compared to the persistence time. So the velocity has decorrelated many, many times. Okay. In the regime where the alpha relaxation time is much larger than the persistence time, the velocity have forgotten everything. So this is really displacement as in equilibrium supercooled liquid. In supercooled liquids, the velocities are totally uncorrelated, yet you have large correlations at large times for the displacements. Okay, so it's the same thing here.
Ask a slightly different question, Ludo. From the experiments, can people, I thought you were done. I'll give it back to you. Can people deduce what the nature of the noise correlations are? Like in the model, you know what the colored noise is. But from the experiments, can they deduce
No, because what you get is the dense system. So you already have the interactive system. You cannot go to the dilute and then. So no, they haven't tried that. They are now studying the dilute limit a little bit more carefully, but no, they haven't done this yet. So I'm not sure that it's. I haven't claimed that the bacterial system is a self-propelled system.
No, I wasn't putting you in the spot. I was just wondering.
And I think it's the opposite. Like they studied 5 or 6 different ones, and 4 of them, I think they go back and forth like this, and then they turn like this. So it's really a different model. Yet if you compress and you look at the emerging behavior, it's the same. Yeah, sure.
Yeah, very quickly. So the change in the tau. Oh, this is tau p.
No, it's the alpha. It's the alpha relaxation time. Yeah.
It's a persistence time.
No, it's really the.
Yeah. So the change is somewhat modest given the density change. Is that because you're still very far away from?
Well, no.
Jam and kill
I have figures I could show you. I mean, if you plot the relaxation time versus density, you'll find the good old divergence that you know well.
So not strong behavior. It is going to be.
Yes.
Okay.
Okay. Thank you. So let me go to the next part, which is about this dense persistent fluid. So I go back to my phase diagram. So I've shown you what's happening when I move horizontally towards large densities way below the MIPS. What I haven't discussed maybe in this phase diagram is this gray corridor here, where you have this fluid region that persists at arbitrary large persistent lengths. So someone asked the question the other day, if you go to MIPS and you do this phase separation, it could be that the dense phase of the MIPS is arrested. If you do the simulation, you see that it's never arrested. So it means the dense phase here is not yet arrested, and then there must be this liquid corridor here. That means in this model, at least, you can increase the persistent length, and if the density is such that you're beyond the MIPS, so you're dense enough to avoid the MIPS, and yet it's small enough that the system is not arrested, what you have is a very persistent fluid. This is what I want to discuss now. So we'll go to these very persistent fluids and look at what you asked before, so the velocity field now. So I'm not looking at displacements, but the instantaneous velocity field. So this is one picture where the direction of the velocity is denoted by an arrow, and the color indicates the amplitude of the velocity. So you have an idea what the velocity field is. Okay, so again, my answer to Shrikant was at equilibrium, if you take a snapshot of this, is white noise because the velocities are totally uncorrelated in space. This is the Maxwell-Boltzmann distribution. So if I show you this picture, you know that the system is out of equilibrium because this should look like uncorrelated field for an equilibrium thermal system. So what I think I want to discuss is in these persistent systems, if you increase the persistence time, and people have measured these things, you see this emerging velocity correlation. So this is measured in units of the particle diameter. So you see these large streams of velocities, you see these vortices. So this is this emerging active turbulence or flow that I want to discuss. So in that model of self-propelled particles, you have large density and you increase the persistence time to make and increase the correlation length of these velocity correlations. And the physics behind this emerging length is really the competition between very persistent particles and density effects, and this is the result of this emerging velocity correlations. So that has been discussed in the context of crystal systems. Silke has discussed this in the context of Aristide amorphous solid, and Jegosh and Elijah have discussed this in the fluid phase itself. Okay, so this is what the velocity field look like now. And the time correlation of this velocity field is directly given by the persistence time I was discussing before. Okay. So if you now look at these people who have done studies of this active turbulence, you can learn how to try and see whether the model that we have with this large-scale velocity correlation resembles a little bit like the active turbulence system that I have discussed. So these are just for illustration purposes, these are the flow lines where you see the large vortices, as in my snapshots taken from the review of Joanny and Allard. So more quantitatively, what people measure is quantities like this, which is inspired by studies in turbulence, where you measure the spectrum of the kinetic energy in Fourier space. So this is the behavior that we see. So at large scale, small distances, what we have is the microscopic distance between the particles. So this is the peak of interparticle distances. As I increase the persistence time, I told you that the correlation length of the velocity correlation is green. So you see this peak that is the shifting towards low wave vector, so large length scale. So this is the green length that I was describing before. And so what we see is that in between these emerging correlation lengths and the microscopic lengths, we see something that is looking like a power law behavior that emerges. And so if we send tau p slowly to infinity, we have this separation of scale between the particle size and these correlation lengths for the velocities that you see visually here. And in between, the system looks like it obeys, or it has some kind of algebraic behavior for the velocity correlations in space. So it's not like turbulence where you have totally scale-free systems. Here, the power law is cut off at a correlation length that we can control, but yet the power law that we see is nowhere in the review by Giovanni and Allard, and it sort of makes sense to me because, as I told you, this is how the correlations emerge. They come from this competition between crowding and persistence, and crowding was never discussed in this previous studies of active turbulence. Okay, so this is the power law that we find minus 1/2. Okay. So now I've showed you the velocity field, and what I want to show you now, just 1 second, is how the particles move along this velocity field. So to show the displacements of the particle, what we've done for this system is we've colored the particles bleu, blanc, rouge. So this is the French flag. And the particles just carry their colors. So what you see is how the particles are moving. And perhaps I have a movie, and then you can ask your question during the movie.
Okay, so this is the question I was about to ask earlier. So if you had gone back to your previous slide, and if you're not showing the movie, so in your slide you said it's now ABPs. Is that correct?
No, it's Ornstein-Uhlenbeck, but ABPs do the same.
Right, because you see one of the references you mentioned is Caprini, and Caprini claims that there is flocking in this system, which means that the correlation length becomes scale-free. I mean, there is no correlation length in the system.
Well, we are always, yeah, I know.
There is no correlation length in the system.
I think the paper you mentioned is they say that there is flocking in MIPS. So here we have a bulk system with no phase separation. We never see flocking. So I'm not worried about the flocking. No, I mean at finite tau p, these systems don't flock, never. So it's not relevant. Okay, I go on. Okay. So what you say is that if you had, again, a Brownian system with none of these velocity correlation, what you would say is that the particles would mix, but you would say that the shape of these things would not move. So here what you see, you see these large packs of particles that are being advected on large length scales. So this is reminding me a lot of the physics of chaotic advection. But of course, you should remember that here we don't impose flows at the boundaries. The particles themselves are generating the flows that allows for this mixing that looks like a chaotic advection to me. So I'm not sure that active turbulence is the right name. I also like to think about the connection to chaotic advection for this system. Okay? And coming to perhaps your question about the flocking transition. So to start and see whether this physics that we had observed for the self-propelled system was a bit universal and could be observed in different models, we have introduced a second model for the following reasons. What we didn't like is to create these large-scale velocity correlations, we had to tune one parameter too large. So you put tau p to 1 million, and you have 1 million correlation lengths. So in a sense, it's a bit too easy. So what we wanted to see is whether it's possible to have emerging persistence. So what we did is we switched to ABPs, as you were saying. So this is the ABP term. And normally ABPs, you have that the angle is rotating with just noise. So what we put here is just a little bit of alignment with the following intuition, is that if you have self-propelled particle with just a little bit of persistence time over the one, if you have a little bit of alignment, they will be flowing together for long times. So by interactions, you can increase the persistence time. So this is the idea. So the idea I had at the time was if we take everything over the one now, can we still see these very long range correlations emerging in the absence of flocking, in the absence of sending one parameter to infinity? And this is the result, which is again showing you this large scale chaotic motion. So everything here is really over the one, maybe equal to one, so far from the flocking transition, a little bit of persistence, a little bit of alignment, and that's it, you have it. And if you measure the time correlations of the velocities, you discover that the persistence time is growing very quickly by changing that number just a little bit. And so what we have is persistent motion, very much like in the self-propelled system, but now it's emerging from the interactions. And it leads to the same physics and the same quantities, and the exponent I was showing you for the kinetic energy spectrum is the same. So it's a different model, not very different yet, but it supports a little bit the idea that the behavior is quite generic. Sorry? Oh, yes, so you have to align with your neighbors, and I is the number of neighbors of particle I. Sorry. Okay, so my last chapter, so these were self-propelled particles. So I want to go to the idea of non-reciprocal interactions as a way to drive the system. And so I want to discuss how, again, introducing non-reciprocal interactions can drive the system towards this collective motion. So these non-reciprocal interactions there are many ways to come to this. So there are many studies at the moment where people have studied the systems composed of A and B particles, and the interactions between A and B particles are non-reciprocal. And you see the emergence of this pattern formation. So Golestanian, Marchetti, and everybody has done this. So what we wanted to construct is an isotropic bulk fluid where each pair of interactions would be non-reciprocal. So what we want to do is we want to break Newton's third law at the level of each pair interactions to have something that looks a little bit isotropic. So this is not totally new, so we got inspiration from models of flocking where people have introduced the idea of vision cones, and the idea is that if a bird is flying like this, it can only see the birds that are in a given angle, but they can't see the birds that are in the back. Okay, so I can see you, but you can't see me, so the force is non-reciprocal. So the way we introduce non-reciprocity, and I'll come back again to it, is by thinking about these particles. They have an eye, so they really see the particles. And this eye is telling me how I should receive a force from a particle. So this is particle 1, particle 2. This is the angle that I see, so this is how I see you. And I'm using this angle to define the force between particle 1 and particle 2. And if this second particle is looking elsewhere, so the angle that this particle is using to feel the force is different. And so F12 and F21 are no longer related by the Newton's third law. Okay? So to do this in a minimal way, this is how we did it. So we say that the force between particle I and j is the same repulsive force as before. So in the absence of this angle term, this is 1. So this is the usual WCA system. So what we introduce is just a small number here with this angle to make the force non-reciprocal. So when nu is equal to 0, this is the good old conservative forces. And when nu is different from 0, the system is no longer conservative. It's no longer the derivative of the Hamiltonian, and the forces are not reciprocal. So this system is constructed in such a way that it is minimal. So it has two ingredients. It has, again, the crowding, the repulsive forces, and it has the non-reciprocity. It doesn't have self-propulsion. It doesn't have noise. It doesn't have anything, just the non-reciprocity. And the question is, if I increase the non-reciprocity, can I give rise to interesting collective motion again? So we don't put anything else but non-reciprocity and crowding. Okay. So this is what we see. So again, when nu is equal to 0, the interactions are reciprocal. So it means, it means that when the interactions are reciprocal, the equation is just r dot is the gradient. So you follow the gradient. So this is a gradient descent. So when the forces are reciprocal and nu is equal to 0, you follow the gradient. And when you are at the bottom in an energy minimum, you stop. This is just gradient descent dynamic. Okay? So clearly, the system is going to find an energy minimum. You will be there, and you won't move anymore. So no non-reciprocity, no motion. Okay? So now the question, what's happening when I increase nu just a little bit? So when nu is non-zero, then I no longer have a gradient. So the only thing I have is the velocity is the sum of the forces, but the forces no longer are the derivative of the potential. Still, it's possible that the sum of forces is 0 and the velocity is 0, and this is what the system is doing. So I think I have a movie of what the system is doing. So you start from a given initial condition. So here you see just the particles, the bare particles. And the black things are just tracers for you to observe what the system is doing more easily. So you put your particles at random and you observe what it's doing. So it's flowing a little bit, and relatively quickly it's going to find a force balance configuration when it's moving as a block. So the center of mass is moving, momentum is not conserved, but no motion at all. So the system still is able to find in a reasonable amount of time a force balance configuration, and it's not moving, reorganizing anymore. Now you increase nu a little bit more, and you have your answer. It's going to flow like this forever. So again, this is a system where you don't have noise, you don't have temperature, you don't have self-propulsion. You only have non-reciprocity as a source of momentum creation. And this is what the system does spontaneously, and it's flowing forever. So it seems to suggest the existence of a transition below which you have no motion, and above which you have these interesting chaotic flows. And again, I repeat, it's only the result of the non-reciprocal forces. So this is a velocity field again, as before. So you see, unsurprisingly from the movie that you've seen, the emergence of this large-scale velocity and displacement fields. Okay, so if we go again through the behavior and the active turbulence system, we have again the very same spectra. And now we tune the this parameter nu, the amount of non-reciprocity. And as we decrease it a little bit and we approach the transition where the system is flowing, we see again this emerging growing correlation lengths with the very same power law behavior here. So we see that again, due to the interactions, you've seen the movie, it's really looking the same as before. We see the same energy last two slides. So is it a transition that has been discussed before? And the answer is a little bit, but not really. And so in my old days, when I was a PhD student, one of the topics was the physics of sheared systems. And the way we attacked the problem was by looking at systems that were, okay, so this is the systems that were undergoing glassy dynamics with non-conservative forces. So this is what we did in this paper. We looked at the same type of dynamic equations that Sarosh has shown on Monday in the presence of coupling constants that were not symmetric. So these ideas were even older because in the context of Hopfield or neural networks, it's very typical to study, again, these neural networks that have non-reciprocal interactions. So there is a range of studies of influence of non-conservative forces in spin glass models or glassy models. And there is all these studies that have studied this problem. And here the outcome from theory, and you can do theory in some kind of mean field limit, the influence of non-conservative forces was so strong that you had chaotic dynamics all the time. So this is why this paper has this title. So an arbitrarily small amount of non-conservative forces was able to make these glassy systems flow forever in the mean field limit. At the end of this paper, we say, oh, in finite dimension, it should be different. Non-conservative forces should be different. It should be undergoing a phase transition. So that is, you should need a finite amount of non-conservative forces to make the system flow. But the calculations in finite D in glassy systems are complicated. So what we see now is evidence that, yes, there is a finite amount of non-conservative forces needed. And it's looking like this absorbing phase transition. And this is my final message. So this is a transition below which the system dies into a state out of which it cannot come back because there is no noise, and above which the system keeps being active all the time. So we use all the tools from these absorbing phase transitions. For instance, one quantity you can measure is the time it takes for the system to find this force balance configuration, and it's growing very quickly as you approach the transition. And you can measure relaxation time in the active system, and they also diverge, and you have this idea of a phase transition. Okay. And the final slide that I have is about can we use even better, like that is the universality class of these absorbing phase transitions. So non-absorbing phase transition all fall in two universality classes. So we have the feeling that this one should be in the conserve-directed percolation universality class. So we try to analyze our chaotic flows in such a way that we measure correlation lengths and we measure correlation times, and we try to see as we approach this critical transition whether the exponents of the CDP universality class could describe our data, and they do describe the data quite well. So we have the feeling that this transition towards the chaotic motion in this system is very much related to the CDP correlation universality class. I think I'm done. So this is my conclusion. So I told you about dense active materials and this interplay between activity and density, asking questions about the origin of these physical motions, and trying to convince you that using very simple particle model can help disentangle the physical effects. Thank you very much.
Silke?
Yeah, thank you very much. So, so it's actually interesting now because we have these sort of length scales, some of them diverge, some of them don't, and it seems to depend very much on the microscopic method you introduce them, what you can get. So just a square tau p, and then you put some alignment, it's still finite, and then this one which becomes infinite. Do you have insight into this?
Well, the insight is what I was trying to say, that is, if you only have one ingredient, which is the persistence time, so you say, I'm taking self-propelled particle, and that's it, no other ingredient. You have just one axis to play with, that is the persistence time. If you now want to have a persistence time that is emerging from correlations, so you can imagine that you have a bit more flexibility, and you can imagine cases where the emerging correlations would be so strong that this time could diverge. So that is my feeling. That depending on the mechanisms, either you impose directly by hand in the equations of motion tau p, and then that's tau p, it cannot really do something else beyond the number that you put, or it's an emerging things, and then it can go wherever it wants.
So when you have this persistent motion in this second or the third type of model, what happens to the dynamical heterogeneity? Does it diminish or remain unaffected?
Again, what are
When you have the persistent motion in the system, does the dynamical heterogeneity diminish or it remains unaffected?
well, I think I can just repeat what I told to Shri earlier. That is, the simplest case is again you put let's say self-propelled particles. You impose a persistence time 10, 100, 1000. You choose, but now this number is fixed. That's your microscopic model. Then you increase the density to go towards the glass transition where you want to see the emergence of glassy dynamics. So persistence time is fixed, but the relaxation time of the system is going to become larger and larger. So at some point when the alpha relaxation time is so large compared to the persistence time, you have a separation of scales. So these velocity correlations, they will decay at the persistence time, and it takes much longer to go to the alpha relaxation time. So the dynamic heterogeneity would be displacement field at tau alpha versus velocity correlations at tau p. They live in different time scales. Okay? So you can have both. You can have persistent velocity correlations, and at longer times, displacements that are strongly correlated because of dynamic heterogeneities.
Last question.
So then following up on that, you have a regime in where you have the velocity correlations present in the fluid before you undergo the
Yes.
arrest. Do you know if they sort of belong to different universality classes, or is there a way of proving that? Like, is tau p equal to 0 as sort of a singular limit, and that there are no velocity correlations? But then if I have any tau p,
Yes.
then is that a different kind of transition?
What do you mean? What transition are you talking about? I mean,
The arrested
Oh.
arrest transition.
well, this is what I was trying to say. I mean, when I say this is a non-equilibrium glass transition, it means if I show you a movie of what the particles are doing, you won't be able to tell the difference. If the persistence time is modest, I show you the compression, I show you the mean square displacement, you can tell the difference. Yet at the fundamental level, it's very different. But qualitatively, the emerging physics is probably still particles are exploring with the column noise, non-equilibrium noise, metastable states, that is long-lived states, and then occasionally they do these jumps over large barriers. It's not free energy barriers or anything, but still the physics is qualitatively the same.
Are there any properties that one can probe to say, oh, the tau p 0 is a different kind of?
Well, I would say it's gradual. I mean, we did, FDT violations, so gradually, smoothly, it goes to 0. But, so again, the physics is changing smoothly. It's just our ability to describe it that is singular.
Okay, so next time Ludovic again. Thank you so much. Okay, so our next speaker will be Prasad Perlekar on emergency asymmetry in confined bioconvection.
While they fix the colors and the mic,
Thank you. So while they fix the color and mic, let me nevertheless start the talk. Yeah. So what I'm going to talk about is a regime which is belongs to the broad area of what the talks have been about this morning, which is the area of active matter. But I'll talk about a regime which is far away from what Ludovic talked about in the sense of extremely dense active matter where you see glassy behavior and other interesting things. What I'll be talking about is actually a collection of what happens when you look at collection of microorganisms which swim. So the self-propulsion part is identical to that of Ludwig's talk. However, I'll be working at concentrations which are much smaller, right? So you won't have all that interesting glassy dynamics and whatnot, but you still have many other effects which we'll see in a moment. And what I will also like to talk about is a system where walls matter. So I'll try to talk about an experimental system where you have walls, and I will show that the presence of walls have a crucial impact on the physics that you observe, right? So that would be in some sense the broad idea of this talk, and this work was done in collaboration with Martin Bayes, who is an applied mathematician doing experiments on these systems at University of York and me, and the paper would be soon out this month. So let's go ahead. So what is bioconvection? It's a collective behavior of gyrotactic organisms. So what is the example of a gyrotactic organism? It's algae, maybe Chlamydomonas. And what you then do is you take this algae, put it in a beaker, right, and wait. And what you start to see is these spectacular patterns which resemble, if you have seen any videos on fluid dynamics, thermal convection. Okay, and the question is, why does this happen? Can we understand it? And there are all the kind of patterns which are similar to cell-like structures which one observes in thermal convection, which is observed over here. And there are nice review articles, and actually this subject predates active matter. So the first papers on these subjects came out in 1980s. I think that's the time where the word active matter itself wasn't coined, and people were already looking at the collective behavior of microorganisms, trying to understand theoretically how could we address this problem. And what I'll again show is that with the insights that one has gained or the methodologies that have been developed in active matter, what all you can do with this kind of things. So let's go ahead and let's first try to understand the organism itself, which is making these kind of patterns when you, instead of working with just one organism, look at the collection of organisms, right? So our hero of the story is this guy algae, which is a Chlamydomonas. Now what is interesting about it is that it senses gravity. So it likes to swim in the direction opposite to the gravity, so it likes to swim upwards. Second is the following, that it's bottom heavy. So its center of mass, it's nearly spherical, its center of mass and center of geometry are not at the same point. What does that do? That if you put this organism in a shear flow like so, then the flow will try to rotate the organism, but because it's bottom heavy, there is a torque which is acting on the organism, which will try to realign it, right? This idea of torques balancing gravitational or swimming of the organisms upward is called gyrotaxis, all right? And what then you can do is you can write a torque balance. So that what is the total torque on this body? Remember, we are working, these organisms are microorganisms, so Reynolds number is very small, inertia doesn't matter. So the total torque, whatever is there, is 0. So what is the total torque? There's a drag term, which is standard drag term. Curl of u is the velocity of whatever flow you have. Omega is the rotational velocity of the organism itself, and this is the torque. Mg is the direction of the gravity. This is the distance of the center of, L is the distance of the center of geometry to the center of mass of the system, right? So that's the net torque on the system. You can solve for it, get an equation for omega, or much more easier, what you can define is an orientation axis which points along the swimming direction. Then you take this, the torque balance equation, do a cross product with the orientation vector, you get a time evolution equation of how does the orientation vector changes in time. That's fairly trivial. And then you have something very interesting. There are two features which you straight away start to appreciate. One is that the organism as expected, is trying to align itself in the direction of gravity. And the second thing is that because there is a vorticity present, it's trying to reorient. Now, because this organism is nearly spherical, we don't have any contributions from the elongation strains present in the system. If you had an organism which was elongated, like a bacteria, then you would have additional couplings coming like lambda s dot p, where s is the rate of strain tensor, which fortunately we need not worry about in this for this simple organism. And just to again keep things clear, it's important to know what are the numbers that you're working with. The size of the organisms, and when I say size, I imply the diameter of this organism, is around 10 micrometers. The typical speeds can vary from 15 to 60 micrometers per second. The offset of the center of geometry to the center of mass is around 0.1 micrometer, and that offset is good enough to now we'll see do very interesting behaviors. But remember, at the scale of the organism, okay, the Reynolds number, which tells you what is the ratio of the inertial forces to viscous forces, is extremely small. So for a single organism, you are really still thinking of it in the Stokesian swimmer regime, right? And another thing to keep in mind is that these organisms are slightly heavier than water. So if they were not to swim, they would sail downwards, all right? And because they can swim, they can also stir the fluid. Now, for the people who are experts in active matter, they would realize that this is immediately, these are contractile swimmers. So they swim and generate the flows. So now, let's go ahead and let's ask, what is it that we expect? So now that we understand what does a single organism do, so let's revise. Swims upwards, because center of gravity is different than center of mass, has torques, slightly heavier than water, would settle. And then swims and generate flows also. All right, great. Then what happens if you take collection of such organisms? Should one study it? Turns out that these organisms or algae are extremely important, and you can actually draw axis which is of concentration, and depending upon what concentration you are looking at, you can look at problems on algal blooms to the problems of bioconvection, and if you go in dense enough regime, you might, but not well studied, enter into the regime of what most of the people here think as active matter. So let's just try to see the concentration axis. If the number of organisms per centimeter cube is less than 10 raised to 4, which situation you are in? You are thinking of lakes, oceans, and you are thinking of typical plankton blooms. There are these beautiful satellite pictures that many of you might have seen of harmful algal blooms at various lakes and oceans. We have studied this problem long time ago. And in this particular regime, these organisms are just passively advected by the flow. You need not, because the concentrations are so small, you need not worry about and the flow turbulence intensities are large enough, you can ignore gravity. You can also ignore the fact that these organisms themselves are generating flows, and then, but just because of the fact that they try to reorient with the local vorticity and have some swimming capability which points upwards, you can start to see this patchy behavior. Various people have looked at it. Then comes this intermediate regime where many people have looked at collective motions of these organisms in lab settings. In this regime, the initial work which was done by Kessler, as I mentioned, this predates the terminology active matter the way we use it, right? So what is important here is that the cell diameter again is 10 micrometers, it's this, but if you take this as the cell diameter, you can very easily convince yourself that the typical separation between the cells is roughly 2 to 50 times their body length. Now why that is important? Because remember I told you that these cells swim. Because these cells are swimming and they are contractile swimmers, immediately you would say that look, they are generating flows which are, or they are generating stresses which are active stresses. And if you have active stresses in a force-free swimmer like this, you will have a velocity field which decays like 1 over r square. But remember, there is also gravity. Because there is gravity, these guys also have drag, and there is also stresslet. The stresslet decays much more slower than the way the active stress decay. And remember, their cell separation is quite far away from each other. Therefore, for what we are going to talk about today, we are going to ignore active stress. And this has been somehow over the last few years a theme which I am working on, where we look at systems which belong to active matter, where activity is coming through self-propulsion of the organisms, and the active stresses are not so important. And this turns out to be another such system where the gravity or the stresslet is the dominant contribution, and you can again ignore the active stresses. And what I'm going to tell you, or rather convince you, that just because of the gravity and the swimming motility of the organisms, you are going to observe all these patterns, right? That's the idea of the talk, and what is the role of the confinement. I won't talk about this particular regime, and we have started to work on it, but that's maybe for some time later. So now how you are going to model such a system, right? That's the next important thing. The model is very, very easy. Remember, I'm thinking of a fluid in which you have microorganisms. Fluid is a Newtonian fluid. These organisms typically live in water, right? So Navier-Stokes equation is a model of the fluid. And remember, these organisms are bottom heavy, so there should be a buoyancy force because of the settling of the organisms. That's put in over here. It's the number density times the volume of the organism times the density difference of the organisms with the ambient fluid times the direction of the gravity. So that's the Navier-Stokes equation. And then there are two ways, and this is again something which was talked about yesterday, how you typically model organisms or a collection of organisms. And you could start to work at the microscopic level, where you try to determine the dynamics of individual organism, or you work at a macroscopic level, where you say, oh look, can I write down a field theory, right? And there was an interesting talk yesterday where one was trying to use the methods in field theory to start from microscopics to get to what is the correct macroscopic behavior. So we'll see whether we could do something like that here, or whether people have already did something like this, at least in this system. So the organisms are the dynamics is very easy. The velocity of the organisms is nothing but the velocity of the fluid at the position of the organism plus the swimming velocity of the organism itself. That's what one typically uses. And remember, the orientation of the organism, I already told you what the equation is, right? We discussed it. How does a single organism swims about? And of course, there is slight rotational diffusivity, but that's all right. Now, another thing you should keep in mind is that, remember, I already told you that we are working in dilute regime. How dilute? That the organism-organism interaction is irrelevant, and the active stresses are irrelevant. Therefore, you don't see any contribution here coming out from active stresses or organism-organism interaction. All right, so you can do this, or you can write down the equations or mathematical model in a continuum framework. Now, the Navier-Stokes part, of course, was continuum, nothing changes there. But if you follow any literature on active matter, you would realize that what you would be required to do is, starting from this Lagrangian picture, you could have write down the single particle Fokker-Planck equation and then start to look at moments of the Fokker-Planck equation. And as Satya was pointing out yesterday, then you would have equation for density, orientation, second moment of orientation, third moment of, and you would have a hierarchy, right? And here, somehow I am writing two equations. So what magic was done over here? The magic was that Martin and others, Pedley and all those people, long time ago, in 90s itself, when they were looking at this problem, they realized that if you start by writing the Fokker-Planck equation and noting that you are in the dilute regime, you could use what is commonly used in fluid dynamics a lot, that start from the Fokker-Planck equation, ask what is the equation for the number density, and use the generalized Taylor dispersion theory put forth by Brenner and others to figure out what would be the correction to the velocity because of the swimming. So you would have in the normal active matter term here Vs times P, where P is the average orientation of the organism. So if you use Taylor dispersion theory, you can predict how does that average orientation depends on the local vorticity, and that's what these guys did. Similarly, you can predict how does the local diffusivity, now diffusivity is not a number but rather a tensor which depends on the vorticity. So how does the local diffusivity itself depend on the vorticity? And that's fantastic, because instead of working with a hierarchy, you have now reduced the problem into just a problem of working with a number density, although the number density itself, all the coefficients itself, now depends upon the gradients of the flows, right? And what they did quite spectacularly well was that all these guys who are applied mathematicians also doing experiments took out a single organism, put them in various shear flows and asked, can we measure the exact dependence of velocity on the rotation or on the local vorticity and this diffusivity tensor, and do a fitting, and at least for Climadomonas, variety of Climadomonas, they have a very weird but still something that you can write down form for how does the velocity depends on the local vorticity, and these are nasty coefficients. No need to worry about what are the exact numbers, but just this is to emphasize that people have beaten this problem to death when you are looking at an isolated swimmer, so you have good handle on what are all these numbers. Of course, you could question the following thing, that the moment I switch on the gravity, all these things could go out of the window, because these equations, the equation for the number density is derived for a simple shear or extensional flow, and how does the single organism is responding to it, right? So when I put in gravity, maybe it works, maybe it does not work. Nevertheless, there are few things important to look at in this mess. First, this velocity, which would be Vs times P, the local orientation if you are working with full equations, when you write it in terms of local vorticity, it is not symmetric. That is, the velocity, so x here denotes the downward flow. So remember, the organisms are trying to align themselves in the direction upward, because u is minus Vsp, and if you take a leading order term, which is a constant, so if I look at the organism velocity here, which comes in the vertical direction, it doesn't feel the vorticity, whereas in the horizontal direction, at the leading order, it feels the vorticity, right? So that's very interesting. It correctly is picking out that it was, if there was no flow and if you had randomly oriented organism, it would turn and move upward, all right? So that's quite cool, and similar analysis can be also done for the diffusivity. So you have now a much more simpler system, and you have a continuum equation where you have coefficients where you are finding explicitly tuned based on some experimental results, or you could do a Lagrangian simulation also. And the first thing that we wanted to know, question?
This equation must hold only when there is a global extensional axis because of the form of D.
Sorry?
Because the form of D
Yes.
tells you that this can only really hold if there is a global extensional axis, right? Because the
Of
D
course,
is
yes.
symmetric and it has the symmetries, because
Yeah.
otherwise there is no anisotropy. And what is sigma?
Sigma is omega by, omega is the vorticity, so it's normalized vorticity, no? So, no, so the point is the following, that I'm looking at a system and there is gravity, right? So these in this particular setting, when they derive this equation, as I pointed out earlier, you assume simple flows. So it could be a shear. So once you say there is an organism in a simple flow, and then you say that there are then collection of many such organisms, how does then the probability density evolves? And that would give you an equation for the number density, no? So that's all there is.
And all the organisms are the same.
Yes. So they are not modifying that. That's why I said that in the limit in which this theory has been developed, you could very quickly question me whether it's valid or not, because I have added this term, and once you have the gravity, the stresslet also present in the system, this equations could go back. But we'll see how good this approximation is. I mean, one of the reasons to go ahead with this is that in turbulence we do these kind of approximations quite often, and they work fairly well. So, okay. So what are the consequences of these equations? So whenever one thinks of consequences, let's think of experiment. So this was the experiment which was done by Kessler, which is quite cool experiment. You have a flow, which is downflow here. So it's a U-tube. And so what you have is flow downwards here and upwards here, and then you have put in these microorganisms inside. And what happens immediately is the following, that remember there is gradient here, there is a negative gradient here, positive gradient here. So if I am a microorganism here, I see a vorticity which wants to turn me inside. Similarly, if I am organism over here, it also wants to turn me inside, and because of this, you would see a flow focusing. So the organisms would try to go towards the center line of the Poiseuille flow. On the other hand, in the upflow region, what's going to happen is if I am organism over here, I will tilt away from the center line. Same over here, so what would happen is all the organisms go towards the walls, right? And this is what is observed in the experiments, that you have flow focusing here, and here organisms go towards the walls. But something more impressive happens is that if one looks at now these things way more carefully, you have secondary instability presence in the system, where these flow focused stream also makes blip like instabilities. There are regions where you have dense concentration of organisms and few organisms and things like that. And then when they go closer to the walls, it seems as if their concentration grows to some critical concentration and then they fall off. So you have organisms all close to the wall and then also peeling off and then falling down when as a collective their concentration becomes large enough such that gravity becomes important, right? So this is the first effect, and for which you can very easily explain it. Of course, secondary instabilities you can't explain in such a qualitative way. But then, like a good active matter practitioner, you could ask a very simple question. That remember, if I take all these organisms, again dilute, and I ask the following thing, that the following base state, u is equal to 0, all the organisms are swimming upwards, is the solution of the underlying equation. All right? Question, is this state stable or unstable? And now again, you can do a very simple hand waving argument where you see that, look, what's going to happen is that imagine there is a teeny tiny perturbation, so that in some regions you have fewer organisms, there are some regions where you have more organisms. And now remember, if that is the case, there is gravity. The region where there are more organisms, they will sink. A collective flock going upwards like so, rather you would have immediately this thing going unstable. All right? The next thing you can do is ask, is this the only instability? Remember, the experiments are done in a confined geometry. There is nothing unbounded in an experiment. So there are walls. But again, these organisms love to swim upwards. If these organisms love to swim upwards, what they would do is they would have a dense layer of cells at the top. And then again, if you have some perturbation, you would set up flows. And these flows can generate large densities which then peel down like plumes as it happens in thermal convection. So the mechanism is different, but if you look at the flow structure, you would feel as if you're looking at an experiment of thermal convection, and then you have what is known as the overturning instability. All right, so all these things were known at some level, and I've given you, let's say, a head start with what one observed at least in the early days, or with a very simple analysis. More recently, people have started to look at this system in much more details by doing detailed stability analysis, all right, of these equations in geometries like vertical pipe or channels. And what they find it is quite remarkable, that if you have confinement, it leads to dramatic effect in the sense that you could have different kind of bifurcations leading to flows where you have organisms concentrating at the center line and also away from the center line, variety of flow states, or you could also explain these various instabilities in the system, all right? And you can even characterize them very, very precisely. What Martin did was very interesting, is that he started to look at the dynamics of these organisms in a very thin Haley-Shaw setup. And what he started to see is that when the plumes form, they're not always at the center line. Actually, sometimes they get formed very close to the walls. And then the question was, why is this happening? Because when people were doing linear stability analysis, they always assume axis of symmetry. So you are not going to figure out whether you have anything which can be asymmetric in nature. And the question, many people typically ignore this by saying that, oh, such a behavior is happening because these organisms are also phototactarian framework. If I want to do simulation, I can also do a Lagrangian framework. So whether the Eulerian and Lagrangian framework agrees. So that was the starting point of our study. And this is the first thing we did. We assume that the system is homogeneous along y direction, and I just want to understand what are the inhomogeneities if I solve this equation that are developed along the x direction, right? So if you do the simulation, you quickly see first that starting from a homogeneous state, there is an instability that forms. And that instability eventually becomes asymmetric spontaneously, right? And the question was, all right, that's quite interesting, because now we are getting a solution which is not a symmetric solution. The initial instability was symmetric, but if I wait for a long time, I get a solution which is asymmetric. Now, this is numerical. Can we do something analytical? Is there a structure inside the system which can allow me to classify all these solutions? So, turned out fortunately that I could do that, and the idea was very simple, that if you look for homogeneous solutions and impose steady state, then these equations, the ones I told you, simplify to something which is still daunting, but it's much more nicer or easier because the time part is gone. And then you impose weak flow approximation, and then these two equations you can further simplify into equation which looks to have something like a Hamiltonian structure to it. And then what you do is you make some simple transformations which are done here, and okay, one could do this in view of time, I won't worry too much about it, but what you end up with a differential equation of this kind where the coefficient C can be explicitly determined, okay, based on your flow parameters and everything, what is the pressure gradient. And I mean, one could have done without it, but if you look, at least I looked at the literature, and it turns out that this is nothing but a quadratic linear type equations, and these equations allow for a first integral. You can also map it onto a Hamiltonian system to figure out that there is indeed a conserved quantity. The first integral has this form where there is only one unknown parameter, which is k, which is the constant of motion. And so if you do a stability analysis, it's trivial to show that you have a fixed point at origin, okay, and then you have concentric orbits, and these concentric orbits are bound by a separatrix which is given by this k. And what solution that we got? You can plot it here in terms of this phase space of V and dV by dy. The dots are the numerical data, and the continuous line is the theory. So it looks like whatever we are doing is not so bad. Things are indeed consistent. Now you could ask the following question, that if you are doing numerics, you can do many more things very easily, right? Because numerics are way easier than experiments. You can impose a symmetry, and if you impose symmetry, then you can find symmetric solutions, again with no flow, where you have a jet, a downward, so positive U unfortunately is downward flow. So you have downward flow at the center, and therefore organisms cluster over here, and two jets, counter jets going upwards, no organisms in this direction. Or you have flows where there is downward flows close to the wall and a central jet going upwards, and wherever there is a downward flow, the organisms will cluster. And indeed all these solutions satisfy these first integral. So that was very nice that we were able to figure out an underlying integral in the equation. Not only that, then you can play the game of asking what happens if you impose an external flow. What happens to the asymmetry of the solution? So what turns out that as you crank up the flow intensity, the solution starts to go more and more towards the center line. If you impose a flow which is, yeah? 5 minutes. Oh, I have 5 minutes, wow. So let me skip this part. If one is interested, I can talk later. But what is crucial part is the following, that you could now compare the Lagrangian and Eulerian simulations, and if you compare the two, they fall on top of each other. So that implies that the simple approximation, I mean, you have to spend some time to get to that equation, but if you do that, that works very well, and the Lagrangian picture within error bars work fantastically well with Eulerian picture. But one could very quickly criticize by saying, look, all this is crazy, you're doing things in one dimension. Well, you can do it in 2 dimensions. And the moment you do it in 2 dimensions, you start to see these blip instabilities. Above is the Lagrangian picture, below is the Eulerian picture. They agree fantastically well. And you also see spontaneously asymmetric solutions emerging in the system. Turns out that asymmetric solutions are more stable than the symmetric solutions. I won't talk about it. But if you then go back to the experiment and ask what happens if I increase the flow rate, if you increase the flow rate, then similar to experiment, you start to see blip-like patterns appearing in the system. You can again do a theoretical analysis to understand it. You also, if you have a flow which is going opposite direction, similar to experiments, you see that first things accumulating near the wall. That's not surprising, but what is interesting is that the simple physics is able to capture also the fact that you would have now locally density is becoming large enough such that they peel out from the walls, exactly like in experiment. So in experiment there was no approximation. In the theoretical analysis there was this very interesting approximations that one made, where one is ignoring the flows, the flows generated because of the individual organism. Still you are able to capture all the features of an experiment, and then we got very happy. We said, aha, everything is working. Let's do something which is even more impressive. So what is even more impressive is that Martin had this very nice Hilly-Shaw setup where you have now confinement in all directions, right? Earlier I was looking at confinement only in one direction. Now we have wall at top, wall at bottom, and also horizontal confinement. And that's interesting. Why? Because remember, wall at sides will give you asymmetry. But if you have also confinement in the other direction, that when something hits the bottom, it will start to see all the walls, and you could have then more crazy behavior. Let's see what happens in an experiment. So in an experiment, they stir it initially slightly, and then you have these plumes forming. And then these plumes stay put. They're not moving that much. So you have plumes, and the plumes are what is referred to in the bioconvection literature as bottom standing. That is, they are not moving around much, like in thermal convection. All right? And now you ask, can I understand this? At least qualitatively. So we said that, look, okay, how do I model confinement? And the answer to that in the other direction, and the answer to that was, as a good physicist, I would use a linear drag model. It works. If you use a linear drag model and you go on increasing the drag coefficient, you start to see something interesting, that at zero drag, you have something which looks very turbulence-like. When you increase the drag coefficient, similar to experiment, you start to see plumes which are very, very stable. However, we are not able to capture the bottom standing plumes which are present in the system. In the experiment, if you increase the confinement more, the bottom standing plumes stop at much earlier level. That's what we observe in the simulations also. However, in all the cases, we are not able to capture the bottom standing nature of the plume, and that we believe is because of the three-dimensional nature of the problem, for which we are still doing some analysis and trying to set up some more simulations. So what I hope I have been able to convince you is that confinement is important. Even when active stresses are not present in the system, when organisms can swim and they have other mechanical properties in them, they can do extremely interesting behavior, right, which is worth looking at. And all the things that we have done, it correctly captures many features away from the walls correctly, but when you are close to the wall, there are still open questions present. And indeed, in the plumes that were forming, it's not at all clear whether the cell concentrations have become large enough that one can still ignore active stresses. So that's another thing that we are investigating now. So with that, I would like to stop and be happy for any questions. Yeah.
Any question? So I was wondering, when you keep increasing the density, you
yes.
said, I'm not going to say anything about turbulence, but up to what point you can go increase the density before you really have to take into account the interaction?
Yeah, so we believe, this is why I showed this picture. We believe it's somewhere here. So if you go to something like 10 raised to 8 to 10 raised to 9 cells per centimeter cube, beyond that, at least for this organism, it looks like that the active stresses would start to become important. And remember, even 10 raised to 8 is not so large. You are talking of volume fractions. So yeah. This regime are volume fractions like 0.01, 0.1%.
This
okay.
regime is the one you are in.
Yeah, that's 0.1. The oceanic flows are even lower. That's 0, right? So the regime which most people work in, it's much more denser than that. So you know, really, if you're 10 raised to 9, 10 raised to 10 cells per, and that you can do mostly in labs. In oceans or in general settings, it's I don't know where. I mean, maybe in dense colonies or epithelial tissues. There, it's of course obvious, but in these swimming organisms, it's not so clear to me.
Okay, thank you.
Prasad, I didn't really follow the last part. These plumes you said, right? These are not because of the gravity for the 4-1?
No, so they are because of the gravity.
So coming and settling down.
Yeah, but the fact that they settle down and keep on standing there, it's not obvious why.
The entire strain.
The entire stretch. It just sits there, right? So if you see the movie, so with all these crazy flows generated, it's not very obvious what's happening at the very bottom, that these structures, you see organism peel off, go up, but this plume lives for a fairly long time. Why?
What is the reason you say?
I don't know. I mean, at least with the drag you can get it, but there's still, there are obvious things which we don't understand because the other, so what is the dimension C? The width, that is this confinement direction, is only 1 millimeter. So it's really extremely confined system, and then, approximating it with a linear drag, is it a good idea or not? We are exploring all that stuff right now.
Thanks.
Okay, so let's think. Oh, we have another question.
So after mapping your model onto the Hamiltonian system, do you have only do you have a fixed point in the thought
Yeah, the fixed point is origin.
origin?
Yeah, so it's exactly like a Hamiltonian system, right, where you would have a fixed point and then you have concentric.
Yes.
Yeah, but it's just that those structures are a bit more complicated.
Thank you.
Okay, so let's take Prasad again. And we'll meet here at 11:20 for the next session.